Some theorems that can be useful when working with polynomials, and the first one is our remainder theorem. If we're dividing by a linear factor, then we can just simply substitute a in to get what the remainder is, and that saves a lot of time. We don't have to do polynomial division. Let's just prove that. There's our division algorithm. If I'm saying the divisor is x minus a, so I could rewrite the algorithm like that. Now if I substitute a in, a minus a is 0, that bit disappears, so it really doesn't matter what the quotient is. I'm left with remainder a. But the thing is this, we know the degree of the remainder is always less than the degree of the divisor, and as we're dividing by a linear factor, that remainder a must be a constant, so it must be remainder x as well. Thus, the remainder x is the same as polynomial a. And there's our answer. There's our proof. Let's just go use it. Same example as yesterday as when we did the polynomial division. If we substitute 2 into that, sure enough we get the same answer we got yesterday, a lot quicker, negative 19. But then that allows us to find the factor theorem, and that's much more useful. If x minus a is a factor, well, if it's a factor, that means there's no remainder. So via the remainder theorem, polynomial a must equal 0. So if we know that polynomial a equals 0, we got a factor of our polynomial. So we're going to show that this is indeed a factor. Substitute in 2, and what do you know? We get 0. And by the way, in an assessment, don't just write polynomial 2 equals 0 and think, I'm going to save myself a lot of time. Show the substitution step. Yes, it is a factor, but now we've got to factorise it. Oh, I've got to work out the other factor. Alright, polynomial division. X goes in x cubed. Well, x squared, multiply, subtract. X goes into 2x squared. Okay, now x goes into minus 15x. And you've got to ask yourself, what was the point of using the factor theorem when I just did this division and ended up with 0 anyway? Why didn't I just do the division straight away? Well, let's just complete my factorisation. Well, the answer is, the reality is, don't use polynomial division. Right? It's x minus 2 times some other factor. It's much quicker to just look at this and do it by inspection. And so we ask ourselves some questions, because what do we know? We know the leading term times the leading term would equal the leading term of our answer. So in other words, x times what I'm looking for here must give me x cubed, so well, that's got to be x squared. And the same thing with the constant. The constant times the constant must give me the constant. So negative 2 times the number I'm looking for must give me 30. That's got to be negative 15. Oh, how many x's do we have? Well, if I was to expand it out now, how many x's would I get? I'd have minus 15x. But I want minus 19x. If I want 19, how many do I still need? I need another minus 4x. Well, therefore, minus 2 must be times something to get this minus 4x. The middle term's got to be 2x. And so we get that same other factor, and we can factorise it down. Now you might think, oh, but surely the polynomial division was quicker anyway. Well, it's up to you how you do it. I mean, you could still do the polynomial division if you want to. Let's do this one. But this time they haven't given us a clue as to what the factor is. We're going to have to use the factor theorem. So we could pick any number we like and substitute it in and hope it turns into be 0. But we want to be logical about this. We know that the constant factors must be a factor of the constant, if that makes sense. What I'm basically saying is the possibilities for the numbers that I'm going to test must be factors of 36. Now I deliberately picked 36 here because it's got a lot of factors. So it could be 1, 2, 3, 4, 6, 9, 12, 18, 36, but of course there could be negative numbers as well. So you can go all negative those. But it's not monic, so you could have fractional factors, and all fractional factors will be in this form. Factors of the constant divided by factors of the leading coefficients. So all of those possibilities could be divided by 4 as well. They are also possibilities. Some of those we already have, because of course 4 over 4 is 1, and 12 over 4 is 3, and 36 over 4 is 9, but we've created some new ones to try. 4 has another factor of 2. They are all possibilities. Some of those we already have, so let's cross out ones we've got twice there. And of course all of those fractions could be negative as well. So these are all the possible numbers we're going to check. We want to pick a logical first first one, or something that's easy to work out. So the easiest one to work out of all of those factors would be which one? Yeah, that's right, 4. No, of course it's 1. But look, 4 turned out to be 0. That was lucky. Hey, I got the right one straight away. No, the reality is you probably would try 1 first and it didn't work, but 4 works. I know x minus 4 is a factor, so what is the other factor? The leading term times the leading term will give me the leading term. So x times 4x squared will give me 4x cubed. The constant times the constant will give me the constant. So minus 4 times minus 9 will give me 36. What is the middle term? If I was to expand that out, how many x's would I have? Minus 9x. How many do I want? Minus 9x. Looks like we've got it then. There is no middle term for this particular one. And of course that second factor, difference of 2 squares, we get 2x plus 3, 2x minus 3. Let's have a look at some HSC questions, what has been asked in the past. So we were given this interesting polynomial. Some factors have been written down and there's some other ones we've got to find. Polynomial x is divided by x plus 1, we get a remainder of negative 11. When it's divided by x minus 3, we get a remainder of 1. What is the value of b? They've told me that when I divide by x plus 1, so in other words, when I substitute in negative 1, I'll get negative 11. Now that's nice for this question because it means that first term is going to be 0, that second term is going to be 0. So actually I'm just going to be left with b. So b is negative 11. What's the remainder when we're divided by x plus 1, x minus 3? Polynomial 3 is equal to 1. They've told me that. Right? Divided by x minus 3, the remainder is 1. I know that. Well, if I was to substitute 3 into my polynomial, the first one disappears. The second one becomes 4a. So 4a plus b is equal to 1, but we have already worked out b, so we can now work out a. A is 3. So what is my remainder? Substitute back in now the a and the b, and I get 3x minus 8 for the remainder. There it is. Okay, we've been given a polynomial and an equivalent expression for that same polynomial. Find a is what we had to do. Okay. Well, I know, looking at the right-hand side, it's written in the form of the division algorithm. And what they're basically saying to me is when I divide by x plus 2, I get an answer of 3. I know polynomial negative 2 is 3. So if I now substitute negative 2 into the left-hand side, I know that's got to equal 3. Playing around with that, we get our value of a. A is 19. This time we're divided by a quadratic. It's been factorised, x plus 1, x minus 4. Quotient is qx, the remainder is rx. Or we like these questions where we have to actually explain ourselves rather than write an answer. Why is the most general form of rx given by rx equals ax plus b? Well, what they're getting at is they want to see if you realise that the degree of the remainder has to be less than the degree of the divisor. My divisor is a quadratic, therefore the most the remainder could be would be a linear function. It might be a constant, but the most it could be is a linear function. So ax plus b, a linear function. Alright, given that polynomial 4 is equal to negative 5, show that remainder 4 is negative 5. There's our algorithm. We're saying polynomial 4, well, if I was to substitute that in, I would just get remainder 4. But we've been told polynomial 4 is negative 5, so yes, remainder 4 is negative 5. Now when polynomial x is divided by x plus 1, the remainder is 5. So now go and find what that remainder is. So remainder 4 is equal to negative 5. That's what we just worked out. That means if I substitute into my algorithm, remember the remainder is ax plus b, we get 4a plus b is negative 5. But we've been given a new piece of information. We know polynomial negative 1 will equal 5. If I substitute that one in, I get negative a plus b is 5. Simultaneous equations. We can work out that a is negative 2, and therefore b is 3. That doesn't finish the question, of course, because it said find the remainder, and the remainder is ax plus b, so it's minus 2x plus 3. We're going to do exercise 10D. I'm just pointing something out here. Remember fractional factors? We don't normally write fractional factors when we express a polynomial. We don't normally write, say, x minus a half. the factor would be 2x minus 1. Basically, the solution to it is that fractional factor.